Each time snow drifts from the sky, it may be carrying more than we think. Not just frozen water, not just weather, but microscopic traces of space itself. Dust that once floated through the dark between planets, now hidden inside fragile ice crystals, settling softly on rooftops, forests, oceans, and skin. Most people never notice. There's no sound to mark it. No flash of light, only the silent arrival of something that crossed interplanetary distances before becoming part of the ordinary world. And that is only the first way winter bends reality. On the coldest nights, frozen lakes can speak in booming echoes that carry for miles. Entire rivers can appear to flow backward against gravity. Lightning can flash inside blizzards where no thunder should exist. Sound can travel far beyond its normal limits, bending through layers of cold air as if the atmosphere itself has rearranged the rules of hearing. Light, too, breaks, stretching into sky-high pillars, perfect halos, floating horizons, and mirages that lift distant mountains into the air. Matter stiffens. Rubber snaps like glass. Wood behaves like metal. The world becomes a colder version of itself that follows unfamiliar laws. But the greatest secret of winter is not what freezes, it is what continues. Beneath snow that seems dead and silent, entire ecosystems remain active. Microbes digest, roots breathe, animals move through hidden tunnels of warm air beneath the snow. Insects remove water from their own bodies to survive as living glass. Lakes reorganize into stacked chemical layers that never mix. And above all of it, winter begins to record. Gases, ash, life, storms, civilizations. Layer by layer, the season quietly preserves the present so it can be read in the future. This is the story of what winter is actually doing to the planet, while most of us only notice the cold. It is not a season of stillness. It is a planetary machine, a living archive, a cosmic courier, and once you see what it is truly moving, shaping, storing, and steering beneath the surface of ice, winter will never look silent again. There's a moment in the cold when the world flips without announcing it. The sidewalk stops sounding like rubber on concrete and starts sounding like glass on grit. Doors shut with a sharper note. Breath hangs heavier. Crossing that invisible line, familiar streets, forests, and shorelines begin to behave under rules that don't apply above freezing. The air tightens. Surfaces go from forgiving to brittle. The same footstep that felt dull yesterday now presses into a rigid network of frozen grains that fracture and rub in quick microbursts. The threshold isn't written anywhere, but your ears detect it first. Take that first step into powder that stayed dry enough, long enough, and cold enough to lock its crystals into stiff shapes. The snow doesn't hush, it squeals. That crisp, squeaking crunch is the sound of tiny ice structures collapsing and sliding past each other, brittle and ready to snap. A few meters away, a plowed curb sounds different, coarser, more granular, as compacted snow transforms into something closer to porous ice. Out on a frozen lake, the quiet is a trick. As temperatures swing from afternoon to night, the sheet stretches and shrinks. Stress loads gather in silence until the ice releases them as a low boom that runs under your feet before it reaches your ears. The lake is not just solid water. It's a tensioned instrument with kilometers of string, storing and releasing energy with every change in temperature and water level below. Lift your head, and the air itself has reorganized. Cold, dense air settles near the surface while a warmer layer floats above it. That stack acts like a boundary. Sound skims under the warmer lid and can reach farther than you expect. A train several kilometers away sounds as if it moved closer. A voice thrown across an empty field rides that guided path and arrives whole on the other side. A dog bark on the ridge travels farther than it did last week because the air is now a layered structure, part lens and part tunnel. Even your own footsteps gain a halo as the sharp high notes reflect from the inversion and fold back. The light gives it away next. Fresh snow returns most of the sunlight it receives. Under a midday sun, the open ground doesn't just glow. It erases shadows that would be deep and clear in summer. Sensors call it high albedo. Your eyes experience it as brightness that makes you narrow your gaze even under thin clouds. That brightness cools the air right above the snow, which strengthens the inversion and tightens the acoustic lens below it. Streetlights switch on, and something odd happens. Vertical shafts of light appear to reach up into the sky. They aren't beams from the lamp. They're reflections from flat ice crystals suspended in the air, each face sending light up and back toward your eyes. A halo forms around the moon when those crystals are arranged differently, a ring set by simple geometry between your position and the ice. When the crystals are plentiful and oriented, the night gains structures that didn't exist a moment earlier, pillars, arcs, faint arcs that cross above like scaffold lines. On the horizon, the cold tweaks distance. Near the ground, light bends through layers with changing temperature. The image of a far tree line lifts just enough to look like it's floating. A building's roof takes on a second wavering edge. The effect feels like a trick of tired eyes, but it's the path the light is taking through stratified air, making small but convincing edits to position and shape. These changes aren't special effects. They are the optical consequences of a reorganized atmosphere, where suspended ice and temperature gradients act together to write new visuals on open land. All of this shares a single cause. As heat leaves the environment, molecules move less. Air becomes denser near the ground. Tiny forces that don't matter in warmer months start to matter. Energy sits in places it would usually pass through. Snow crystals hold shape. Ice sheets hold stress. The sky holds layers. The result is a landscape that doesn't just look wintry. It operates in a compressed thermal state. Sound travels differently because the gradients bend it. Light redistributes because crystals scatter and reflect it. Surface textures change because frozen grains deform by breaking rather than by flowing. The same physics you already know are still here, just shifted into a regime we only meet a few months each year. That shift is why footsteps squeal in 1 hour and soften in another. The friction between rigid grains produces a fast, high-frequency burst when they shatter and slide. When temperatures climb near freezing, those grains round off with a thin film of meltwater, and the squeal fades to a damp thud. The lake's boom follows the same rule. A small temperature drop shortens the ice plate, ramping up tension across cracks and weak points. When a crack runs, the energy release propagates as sound that speed matches along the plate, sometimes outracing the audible boom with a shimmer of higher tones. Even the city's glow changes course. Snow returns light upward, and low clouds reflect it back to the ground. Nights under cold, overcast skies look brighter than clear ones. Not because the sky adds light, but because almost none of it gets absorbed by the surface. In rural areas, that effect makes distant towns leave a soft dome of color on the horizon. In valleys, the combination of reflective snow and an inversion traps the brightness near the ground, creating a lit ceiling. These aren't isolated curiosities. They are the everyday signatures of energy being stored, routed, and released in different ways at low temperature. Your breath doesn't vanish. It condenses into visible droplets that show how saturated the air has become. A wool hat muffles your hearing more because sound loses higher frequencies, faster in still, cold air close to the ground. Car tires drum with a harder note because the rubber compounds have stiffened and no longer damp vibrations in the same way. Every sense reports a small departure from the rules you expect. Stand still for a moment and you can read the state of the air. If the snow squeaks, if the horizon lifts, if voices carry, the surface layer is cold and organized. If the sound is dull and the distance wavers less, warmth has returned to the first few meters above the ground. The world is telling you how its molecules are moving, how much energy is available, and where it's stored. Cross that invisible line one more time, and the cues vanish, replaced by wet snow, thicker air, and quiet pavement. This threshold matters because it sets the stage for what comes next. If sound bends and light builds itself into pillars when the temperature drops, then the objects we rely on every day are also shifting their behavior under the same conditions. Materials that seemed steady start to creep or snap. Mechanisms fall out of tune by amounts too small to see but large enough to feel in the way doors stick and rails ping. The cold isn't just an absence, it is an active agent, reshaping not only what we hear and see, but what things are willing to be when the heat is gone. Cold doesn't arrive like a number on a thermometer. It acts like a quiet force, pushing atoms and molecules into tighter order, stripping motion away until familiar materials lose their usual habits. The moment heat drains from matter, bonds tighten, vibrations fade, and everything you thought you knew about how objects behave starts to shift. The changes start small, distances between atoms shorten by fractions of a nanometer, but the consequences add up across beams, roads, tools, and the things we hold in our hands. Cold turns behavior we trusted into something conditional. It rewrites how matter responds to stress, friction, and impact. Take rubber. At comfortable temperatures, long polymer chains slip past each other. They stretch, rebound, and swallow impacts. Drain the thermal energy, and those chains lock into place. The same rubber band that stretched yesterday can crack today with a dry snap. The soles that gripped pavement now lose traction as the compound hardens. Tires that felt sticky in summer become stubborn in winter, their contact patches shrinking while the rubber-glass transition creeps into the range we actually experience outdoors. Plastics follow a similar arc. Without thermal motion to cushion stress, the long chains can't rearrange fast enough under load. A plastic clip that once flexed to hold a panel may fracture along a clean, bright line. Thin housings contract unevenly, creating hairline gaps where cold air leaks in, and fasteners loosen a quarter turn. The identity of these materials was never fixed. It was borrowed from the heat inside them. Metals tell the same story with a different accent. In steel and iron, atoms sit in neat crystal lattices. As the air cools, the lattice spacing contracts. Bridges announce this with quiet voices. A groan here, a ping there, expansion joints that reveal why gaps exist at all. Tracks that ran true in summer pull inward, changing alignment by millimeters that matter to wheels traveling at speed. That movement comes straight from the coefficient of thermal expansion, an engineer's way of saying how much length changes per degree. A single rail can shrink by centimeters across a deep cold snap. Multiply that across a network, and the geometry of motion shifts. Straight becomes slightly bowed. Tolerances, once generous, feel tight. Precision machines don't escape. Microscopic spacing inside gears, bearings, and housings compresses enough to drag on parts designed to float on thin films of oil. What moved with fingertip pressure now fights you as viscosity climbs and clearances narrow. The effect doesn't announce itself with drama. It shows up as startup torque that spikes, motors that draw more current, and timing that slips by fractions. Cold redefines friction. Oils thicken as their long molecules tangle more easily, resisting shear. At the same time, surfaces that looked smooth under light start to act rougher because lubricants can't fill the valleys as well, and the boundary between metal and oil tightens. Machines develop a winter accent even when you treat them the same way you always did. Coatings reveal another layer of this quiet rewrite. Paint clings to a surface that shrinks beneath it. If the substrate contracts while the coating can't keep up, stress concentrates in tiny arcs that turn into cracks. On masonry and stone, the story becomes hydraulic. Water seeps into microscopic pores during a thaw. When the next freeze arrives, that water expands by about 9% as it turns to ice. There isn't room. Pressure rises inside those pores until the rock yields along planes of weakness. Over cycles, sharp surfaces crumble to grit. What we call frost wedging turns a cliff face into sediment one cold night at a time. Soils hold even more surprising power. Frost heave doesn't just lift, it organizes. When water migrates upward through capillaries to a freezing front, it deposits into layers called ice lenses. These grow by feeding on liquid from below. As each lens thickens, the soil swells vertically, carrying everything above it. Roads buckle into waves, fence posts tilt with no sign of the force that moved them. Foundations shift out of square even when the concrete itself remains intact. The pressure exists in the geometry of ice more than its mass. What looks like still ground is quietly rearranging. Wood, even in a dry climate, always carries moisture inside its cells. In winter, that moisture can freeze, turning flexible fibers into rigid struts. Vibrations that once faded quickly now ring longer and travel farther. A plank you could bend slightly without worry becomes stubborn and brittle, more likely to split along the grain when struck. The stiffness increases because the water inside the cell walls transitions, changing how the structure carries load. Joints that felt snug in autumn settle as shrinkage reduces width across the grain. A door that closed softly now rattles. A step that muffled footsteps now sends a sharper, faster sound. Cold also changes the way materials share forces with each other. Composite parts with different thermal expansion rates start arguing at their seams. Aluminum contracts more than steel. Plastic contracts differently than both. Bolts loosen or overstress depending on which component moved more. A gasket that sealed at one temperature can wrinkle or tear at another. The design worked in the lab across a narrow range. Winter widens the test. Even glass responds. Take a pane warmed by sun on one edge and cooled by wind on the other, and you set up internal stress that can find a flaw and run it end to end. The same rule applies underground, where materials we don't think about take their turn. Buried pipes see the soil around them change volume, loading joints differently. Plastic water lines stiffen, reducing their ability to absorb shock when flow starts and stops. Metal conduits contract, opening tiny gaps that allow groundwater to creep where it shouldn't. In all of these cases, cold orchestrates a change not by pushing hard, but by removing energy so the system settles into a new arrangement. The force is absence, working like presence. Look again at a mechanical assembly in deep cold and you see an ecosystem. Shrinking housings squeeze bearings, thickening oil increases drag. Rubber seals harden and leak. Plastic wire insulation stiffens and transfers vibration into connectors. Metal brackets contract and rotate the entire setup by a fraction of a degree. These tiny shifts add up to function that drifts out of tolerance. The machine didn't break. It became a different machine, built from the same parts but held together by altered physics. On the surface, the changes feel inconvenient. A brittle phone case, a stubborn latch, a road that suddenly hums through your tires. Inside the materials, the shift is precise. Thermal energy controls how easily bonds stretch and rotate. Remove it, and flexibility converts to brittleness, clearance to interference, adhesion to fracture. The lesson is simple but reaches everywhere. What an object is depends on the heat it holds. Some designers counter this by choosing formulations that keep mobility at lower temperatures. Rubber compounds can be tailored so their glass transition sits well below the coldest expected day. Plastics are blended to resist embrittlement. Metals are selected and shaped to accommodate shrinkage, with slots where rigid connections once stood, and with expansion joints placed where stress prefers to hide. Lubricants are graded for winter, built to maintain flow and film under shear when the thermometer drops. The point isn't to defeat cold, it's to decide in advance how matter will forget itself and then remember only what you want. Even with planning, cold finds the weak link. A protective coating that traps a thin film of moisture against stone will still invite frost expansion beneath. A concrete slab poured without air entrainment can still spoil as trapped water turns to ice and pops the surface from within. A cable stretched taut in mild weather hums like a string in Arctic air as contraction increases tension and the wind finds its resonant frequency. A hinge pin that rotated easily in autumn strains as its bushing grips tighter. None of these failures are surprises to the physics. They're only surprises to us because warmth hid the dependency. Out on the street, the signs show up everywhere. A manhole cover rings sharper when a car passes over it because both the cast iron and the air beneath it transmit sound more efficiently. A bicycle chain squeaks through congealed grease, then quiets after a few minutes as friction warms the metal just enough to thin the film. A steel gate that hung level now drags the ground because the post's footing rose on a lens of ice that grew unseen through the week. The world behaves as if someone adjusted a control you can't see. Now the force extends below the white surface, where it looks like nothing happens. Ice crystals grow in soils with water fed from below, pushing upward as they organize into lenses. Roots feel that lift as tension at their tips and sides. Pavement slabs tilt against each other, transferring load along new lines. In the gap between snow and ground, pressurized layers form, break, and reform, creating a slow, hydraulic rhythm at a scale too small to watch and too strong to ignore. As frozen soil raises whole sections of road and cracks creep along buried structures, the direction of attention shifts with it, downward into the quiet zone under the snow where, despite the cold, life's work continues without pause. From above, the world looks paused, white spreads in every direction with no tracks, no movement, no sound. But under that crust, a narrow gap forms between the snowpack and the frozen ground, and it stays warm enough for life to keep working. The snow itself builds the walls and roof. It traps heat from the soil and slows the escape of warmth into the night air. That gap has a name in science, but out here it functions like a small, steady basement for the entire landscape. Snow turns out to be better insulation than most things we build. Each flake locks in air. Piled together, those pockets block heat loss the way a thick down coat does. The air above might die far below freezing, but a foot of snow can hold the ground close to 0 degrees Celsius. That difference decides whether roots survive, whether microbes keep cycling nutrients, and whether small animals can move and feed through months that look empty from the surface. The white blanket prevents violent temperature swings that would shock soils and slow the chemistry that plants and fungi rely on when everything thaws. Inside that gap, an underground highway system comes to life. Voles, mice, and shrews chew and shove their way through the base of the snowpack, tunneling between caches of seeds and stems. They leave junctions and chambers, winter versions of crossroads, with exits that open into short, risky dashes up to the surface for fresh food on warmer days. From above, it's seamless white. Under the skin, it's a map dense enough to confuse a predator that breaks through by chance. The roof mutes noise and hides scent. The animals learn the routes by repetition, by whiskers, by the way vibrations move through frozen crust and powder. Sight barely matters down there. Memory does. The insulation changes the rules for sound and smell. Odors that would hang in open air get trapped and diluted in the snow layers. A fox searching for a vole hears more than it smells, listening for faint scrapes on ice crystals or soft thuds of a body shifting in a tunnel. Prey species change their behavior to fit the new physics. They pause longer, move in bursts, and use short side tunnels as decoys. The whole sensory game resets because the medium has changed. Plants don't sleep the way we think they do. Roots keep exchanging chemicals with soil microbes at low levels all winter. Signals continue to pass between fungi and roots as sugars drip out and nutrients drip back in. It's slow, but it never stops. Even in darkness, bacteria and fungi break leaves and stems into simpler compounds. carbon frees up. Nitrogen moves into forms that plants can use later. Those reactions set up the spring flush before the first meltwater even reaches the streams. Microbial communities adapt to the cold by shifting which enzymes they use and how they build their cell membranes. They conserve energy, but they don't quit. Decomposition under snow keeps soil from turning chemically stale. If the blanket failed and the soil froze hard to depth, microbes would stall, and the surge of spring growth would arrive thinner and slower. Instead, the system idles in gear. It holds its place, fueled by what autumn left behind. The snow layer also changes water's path. Because the ground under snow stays near freezing instead of plunging colder, the timing of melt and infiltration shifts. That can redirect how groundwater recharges and where it flows to streams later in the season. A thick snowpack delays the release of water, spreading it out and smoothing peaks that would otherwise erode soil and wash away nutrients. The delay matters to roots that sit near the surface, waiting for stable moisture rather than a quick flood. Even frozen streams and ponds carry on. Beneath ice, aquatic insects feed slowly through the short days and long nights. Oxygen filters in through cracks and through thin spots where light reaches algae that continue photosynthesis near the underside of the ice. It's minimal, but it's enough to keep the base of the food web alive until breakup. Fish adjust their activity to pockets of higher oxygen. They wait out the winter in layers that rarely mix, moving when they need to conserve energy. In the subnivean zone, heat from the ground creeps upward and hits the cold base of the snow. The first few centimeters of snow often sinter into a dense layer as crystals bond, and the temperature gradient reshapes them. That layer serves as a ceiling for tunnels. Above it, lighter grains hold more air and insulate better. The structure of the snowpack matters to everything below. A powdery, deep cover is quiet and forgiving. A thin, crusted cover is noisy and dangerous, amplifying each footfall and cracking under weight. Plants take advantage of the steady temperatures to protect buds that formed long before the first frost. Snow bends and covers low branches, reducing desiccation from dry winter winds. Small shrubs ride out the season under a dome of snow that keeps tissues from freezing past their thresholds. Come spring, those buds open fast, because the parts that needed to be protected never faced the worst cold. The blanket bought time. Predators adjust to the new rules. Owls strike by sound, punching through the roof to grab a mouse that never saw it coming. Weasels run the tunnels themselves. Their long bodies slip into the network and turn the architecture against its builders. The chase squeezes through turns that no larger animal could follow. Down there, a body length advantage can matter more than speed because speed means nothing when a tunnel dead ends into packed ice. For all the activity, waste heat from bodies and microbes barely changes the temperature. The soil provides the baseline warmth. The snow holds it. If air temperatures crash, the gap narrows but persists. The edge where snow meets ground can frost over and then reopen as animals push and breathe. The system is fragile in structure and sturdy in function at the same time. A single warm rain can collapse it. A week of dry cold can harden it into a shell, but as long as snow remains, the engine keeps turning. The chemistry below differs from the open air above. Moisture saturates the space as snow sublimates and refreezes. That humidity prevents plants and animals from drying out the way they would in exposed wind. Ice grains grow and reshape, and the lower layers of snow slowly transform, but the tunnel walls persist because animals maintain them. Each run reinforces the root, sealing it with compacted crystals that resist collapse. The more it's traveled, the more it can be traveled. Nutrient movement continues in slow arcs. Fungi shuttle nitrogen across soil microzones. Bacteria free phosphorus, bound up in organic matter. These elements don't sit idle. They change hands, change states, and get positioned for roots that will wake. When the thaw comes, the system doesn't need to start from zero. It accelerates from a rolling start. The snow was a pause button for us, not for it. Even the quiet above depends on the busyness below. The lack of visible motion on the surface partly comes from success underground. Animals don't need to risk crossing open fields if the tunnels deliver food and shelter. Plants don't show new growth because the work they need most happens out of sight at the root-soil interface. What looks empty is a mask over a constant exchange. And yet, this protected layer has a ceiling. The higher we go back toward the surface, the more the cold reasserts itself. The air thins, the insulation weakens, and the rules of the subnivean world give way to the exposed domain where wind strips heat, where scent returns, and where nothing is buffered. Up there, survival demands different strategies. Bodies must change, chemistry must shift, and biology has to be rewritten to match the extremes. While most animals retreat from the cold, a separate strategy unfolds quietly. Bodies that stop resisting winter and start matching it. Some insects begin weeks in advance, moving water out of their cells until their tissues become so dry that ice can't take hold. They aren't truly desiccated. They're tuned. What little fluid remains shifts into a syrup of sugars and specialized proteins that change how freezing begins and spreads. The body turns from a place where ice is a threat into a structure that controls where crystals can grow and where they cannot. Their surfaces harden, their metabolism drops, and they hold a kind of stillness that isn't sleep or death, but a paused, state-engineered molecule by molecule. This path looks dangerous because it is. Remove too little water, and ice forms inside cells, tearing membranes. Remove too much, and cells collapse. The margin is narrow. The chemistry must land in a zone where proteins remain folded, membranes remain flexible enough to restart later, and enzymes sit on standby without drifting into random reactions. It's a balancing act performed at the edge of physics, where heat is scarce and motion slows down. Organisms make that edge livable by changing not only what is in their blood and tissues, but how those substances behave when the thermometer drops below freezing. Some amphibians make a different trade. Wood frogs allow ice to spread through the spaces between their cells while shielding the interiors. As temperatures fall, their liver floods their circulation with a surge of glucose that acts as a cryoprotectant. Water is pulled from the cells themselves into the spaces outside, where it freezes first. Inside, the higher sugar concentration lowers the freezing point and stabilizes membranes. The frog's heart goes quiet. Breathing stops. Yet the architecture of life remains in place, protected by concentrated sugars that keep proteins from twisting out of shape. When spring warmth returns, the ice melts, fluids move back into cells, and the heart resumes. The animal had not died. It had suspended the normal rules of being alive long enough to outlast the freeze. At the far end of this spectrum, Arctic ground squirrels let their core temperature fall to levels that would kill most mammals. Their metabolism slows so much that minutes pass between breaths and their heart barely moves. They enter torpor in cycles, briefly warming at intervals to maintain critical functions before slipping back into a state near freezing. The key is precision. Cellular machinery reduces activity to almost nothing without crossing into disorder. Energy use drops to a fraction of normal. Fuel stores shift toward fats that burn cleanly and slowly. The animal remains intact by constantly managing a boundary between ice and liquid, motion and stillness, activity and conservation. The woolly bear caterpillar takes the chemical route so far that its internal fluids effectively become anti-freeze. Specialized proteins bind to tiny ice crystals and block their growth, keeping them from expanding into sharp lattices that shred tissues. Sugars and other cryoprotectants replace water in critical spaces, turning cell interiors into glass-like matrices that hold structure in place. The caterpillar can spend months hard frozen, then thaw and continue as if the pause were an ordinary night. That isn't just survival. It is a reversible transformation written directly into the physics of water and the chemistry of life. Not every winter adaptation is about freezing. Migrating birds commit to a moving redesign. During long flights, they alter the balance of their own organs. Digestive systems shrink when food is limited aloft, reducing weight and freeing energy. Flight muscles enlarge, packed with mitochondria and blood supply to sustain continuous work. Hormonal signals drive these changes, and the body complies mid-journey. The organism becomes a machine for flight through cold air, then later reverses the process when feeding resumes. It's not improvisation, it's scheduled reconstruction. Hibernating mammals appear to sleep, but the internal choreography is exact. Their bodies change how cells burn fuel, switching pathways to maximize energy from fat while minimizing the production of damaging byproducts. Ion pumps in cell membranes slow. Body temperature drops, but not randomly. It settles at levels the organism can maintain safely. The brain doesn't shut off. It reduces activity to the minimum required to coordinate the system. Periodic arousals restore fluid balances, repair tissues, and retune electrolytes. The animal gives up speed and responsiveness in exchange for stability and endurance across months when resources vanish. All of these strategies share a theme. Winter reaches inside bodies and rewrites what they are for a time. It turns water, usually life's medium, into a hazard to be moved or managed, then turns sugars and proteins into shields, glues, and brakes. It converts motion into order by removing heat, and organisms meet that pressure by becoming less like themselves and more like states of matter. Glassy, gel-like, slow. Consider how fine the timing must be. If glucose floods tissues too early, cells may swell or chemistry may run off target. If antifreeze proteins arrive too late, ice spreads uncontrollably. If the torpor cycle in a hibernator stays down too long, wastes build up and membranes fail when warmth returns. The margin for error is measured in degrees, ratios, and minutes. Yet populations persist because these schedules are under tight control, guided by daylight length, temperature cues, and internal clocks that keep time even when almost nothing else is moving. This is also an engineering problem solved without machines. To move water out of cells safely, membranes need channels that respond to cold and solute gradients. To keep protein stable at low temperatures, cells alter the composition of the surrounding fluid and the lipids in their membranes so they stay flexible. To drop body temperature without triggering clotting or arrhythmias, mammals shift electrolytes and blood flow patterns, cooling from the core outward in orchestrated steps. None of these changes are accidental. They're rehearsed each year in individuals and refined across generations. The cost of these feats is paid in trade-offs. A wood frog that survives a freeze carries the burden of managing blood sugar levels that would be dangerous in other contexts. A caterpillar that invests in antifreeze compounds grows slowly because that chemistry is expensive. A bird that sheds digestive mass must find a way to rebuild it quickly upon landing. A ground squirrel that spends months in torpor comes out with muscles that need time to recover function. Survival across winter is not free. It is a deferred expense paid in reconstruction when warmth returns. There's a sensory dimension to this as well. Inside snow-covered forests, an animal's hearing and smell shift with temperature and humidity, so navigating the season requires more than chemistry. Yet the core story remains inside the body. The cold pushes the physical boundaries, and life answers with strategies that change the meaning of alive, without crossing into death. Metabolic heat is no longer a constant. It becomes a resource allocated by need. Water becomes a structure to move, shape, or avoid. Proteins stop being parts that only build and start acting like guardians that block ice and hold form. What makes these strategies so striking is how close they sit to limits. Ice, when it forms inside a body, is usually catastrophic. Yet wood frogs keep it to the spaces where it won't tear membranes. Organisms typically die when their core temperature sinks too low. Yet ground squirrels guide themselves to that threshold and hold position. Cells depend on a watery environment. Insects drain enough of it out to eliminate ice, then carry on months later. And birds, made to eat and fly, choose one function for a time, reshape for it, then reverse. Winter forces choices, and life answers with temporary identities. By the time late winter sun returns, these systems are set for reversal. Sugars dilute, antifreeze proteins degrade, membranes switch back to warmer formulations, and metabolic engines spool up. The lesson isn't that life is fragile or tough. It's that survival becomes a calculation conducted at the molecular level, where every variable can be adjusted. How much water to keep, what fuel to burn, what temperature to hold, when to wake. Winter doesn't only test organisms from the outside, it reaches in and changes their settings. As these altered bodies exhale into the cold, the air they breathe moves through a sky that has been rebuilt by temperature, weight, and chemistry, and that quiet rearrangement will decide what they inhale next. On the stillest winter nights, the air stops behaving like sky and starts acting like a container. Cold, dense air settles into streets and valleys, and a warmer layer rides above it. That layered stack creates an invisible boundary you can't see, but you can feel. Sounds hang lower, breath looks thicker, even smell changes. The lower layer doesn't mix with what's above, so everything that enters it stays put. The atmosphere becomes a transparent lid set on the landscape, and under that lid, the rules shift. Temperature inversions form because cold air at the surface becomes heavier than the air overhead. Under normal conditions, warmer ground heats air from below and lifts it, letting pollutants rise and mix. In winter, the ground chills enough that the opposite happens. The lighter, warmer air rests on top, the colder air sinks and spreads, and turbulence fades. Without that churn, chimneys, tailpipes, and stacks release gases into a zone that refuses to dilute them. The result feels quiet, but the chemistry gets busy in its own way. This trapped air grows chemically distinct from the free-flowing atmosphere above. Emissions that would disperse on a breezy afternoon instead collect by the curb. The mixture becomes its own seasonal recipe. Exhaust and wood smoke, traces from heating oil, fingerprints from industry, all suspended at breathing height. Even the timing of traffic and the morning startup of boilers shows up in the air as small, regular spikes that rise into the lid and then go nowhere. You inhale an environment with a different composition than the open sky a few hundred feet up. Vehicle exhaust lingers like a low tide that never drains. Nitrogen compounds and fine particles hang in place and build a cold haze that sits between your eyes and everything else. Streetlights look dulled. The beam spreads out in the haze and loses clarity, but edges in the distance can sharpen in a counterintuitive way because the layered air bends and flattens sound and light paths. Industrial plumes that would fan away in summer sink back toward the ground and smear along the lid, so their footprint widens even as their height shrinks. Inside this quiet air, chemistry changes speed. Many reactions slow because molecules have less thermal energy. They collide less often and with less force. But some processes benefit from stillness and proximity. When the air doesn't mix, reactants sit near one another longer. Certain transformations proceed more efficiently as the atmosphere holds them side by side. That creates a different pathway for pollutants to evolve, a winter mode of chemistry that trades speed for persistence. Natural systems shift their signals too. Frozen soils don't stop breathing. They vent gases through narrow channels and cracks, pulsing small bursts into the air that then remain trapped. Vegetation produces chemical markers even in dormancy, and those compounds stay local under the lid. Lakes store carbon dioxide and other gases beneath the ice. Occasionally, they exhale through openings or weak spots, releasing pockets into the inversion where they drift sideways rather than up. Each source writes a line into the season's temporary script. You can watch the optics of this chemistry on clear evenings. The haze desaturates color, giving city light a muted cast, while the layering can let faraway signs or skylines appear crisper along certain lines of sight. It looks like a contradiction, but it comes from the same structure. A smooth, stable atmosphere that bends waves predictably and holds particles in a thin slice near the surface. What you see depends on which slice your view passes through and how the lid has set over the terrain. Even your breath fits the pattern. Exhaled water vapor condenses more readily in the chilled, saturated layer. You see it hang and drift low rather than rising and disappearing. That same moisture changes how reactions run on particle surfaces. Tiny droplets and soot act as platforms where gases stick and meet. Under cold conditions, those surfaces become stages for slow, ongoing chemistry. The air is not just carrying compounds from place to place, it is hosting them. Heating systems add their own rhythm. Every furnace cycle pushes out a new pulse of gases that climb a few meters and then stall. Over hours, those pulses accumulate into a background that grows thicker until a change in wind or a shift in temperature shaves the top off the lid. You can feel that change when a faint breeze returns and the air smells cleaner within minutes. Until then, the neighborhood's emissions and natural exhalations remain inside a shared container. In valleys and basins, the effect deepens. Cold air drains downslope at night and pools in the lowest ground, thickening the inversion from the bottom. The lid then follows the shape of the landscape like water filling a bowl. Higher ridges may sit in clear air under stars, while the town below sinks into haze. The boundary can be sharp enough that you cross it in a short drive and the world changes quality. Sound brightens, smell clears, and the sky opens. Chemical reactions respond to these layers in measurable ways. Some nitrogen oxide processes slow as temperatures fall, altering the balance that would otherwise create ozone. In the calm air, fine particulate matter accumulates faster than it's removed. That, in turn, changes how light interacts with the air mass, which feeds back into surface cooling and helps the inversion persist. Winter turns the atmosphere into a slow feedback machine, where physics and chemistry hold one another in place. Beneath ice, lakes run their own chemistry, and the inversion above them acts like a cap on a cap. Carbon dioxide can dissolve into cold water more readily, and microbial activity continues at reduced rates. Gases rise into the small headspace under the ice and wait. When fractures open or pressure shifts, pockets can escape into the trapped air outside and stay there. Each release becomes a small local enrichment that would vanish quickly under summer mixing but persists now, changing the profile of the air just above the surface. Snowpack adds another layer. As a porous blanket, it filters and slows the exchange of gases with the atmosphere. Vapors migrate through it in narrow paths, and when they emerge, they join the inversion's reservoir instead of dispersing into open sky. The snow holds temperature steady just enough to prevent spikes that would break the lid. The whole system acts like a temporary storage array, with each surface, pore, and layer holding molecules longer than usual. In urban canyons, the effect compounds. Buildings block sunlight, keeping streets colder through the day, which helps the inversion reset each evening. Exhaust gets trapped at pedestrian height. The cold haze mutes the glow of signs, and the sound of traffic travels farther down the corridors. Even the pace of corrosion and deposition on outdoor surfaces shifts as the trapped air bathes them in a steady chemical bath. Winter concentrates what summer spreads. The quiet can feel clean, but the chemistry says otherwise. Fine particles and gases assemble into a mixture that behaves like a slow liquid pooled in the lowest air. You share that pool with every chimney and engine around you. The sky above looks clear because the boundary sits below your line of sight. yet your lungs are inside the container, taking samples with every breath. Winter air doesn't just pass through you, it waits with you. When wind finally arrives or a front moves through, the lid peels back, the cold pool drains, the layers mix, and the trapped chemistry spreads out and dilutes. Until that moment, the inversion has held onto a day's worth of emissions and a night's worth of natural signals. The release can reset the local atmosphere in an hour, but during the calm, the sky performed a different job than most days of the year. It stored. All of this builds pressure in another sense. With air stratified and saturated with ice crystals higher up, clouds running over cold ground can process charge in unusual ways. The same systems that slow and store chemistry also set the stage for storms that carry an electrical twist. The atmosphere holds its layers, energy separates inside the cloud, and a quiet street under falling snow becomes a place where light can crack open the sky without warning. Snow can fall so hard that the world goes quiet, and yet inside that hush, a flash can bloom, muted, spread out, almost gentle, followed by a low roll that travels farther than you expect. It feels wrong at first. Winter is supposed to dampen sound and soften light. But in these rare storms, electricity breaks through the snow like a heartbeat under a thick blanket, turning a silent landscape into a charged one. The contradiction lingers in your ears. The air feels packed, as if the storm is storing something it cannot hold much longer. This is thundersnow, a winter event built from collisions you can't see. Inside the cloud, snow isn't floating down in peace. It's a workshop of ice fragments grinding past one another, supercooled droplets freezing on contact, and soft hail, graupel, carrying charge with every hit. The storm sorts itself into zones of positive and negative regions, as if a battery is assembling in mid-air. Updrafts lift lighter crystals, downdrafts drag heavier pellets downward, and friction transfers electrons until the balance tips too far. The discharge has to happen, even if the world below feels like a library. Those flashes look different for a reason. Summer lightning cuts sharp lines across humid open air. Winter spreads the light. Snowflakes act like countless small scatterers, each one turning a clean bolt into a diffuse glow that lights a storm from the inside. Instead of a jagged streak, you see an illuminated volume, a pale shape sliding through white curtains. It can be hard to pinpoint where it struck, because the storm itself becomes the lamp. Thunder behaves differently too. Cold air changes sound. Temperature layers form a kind of acoustic guide that bends low frequencies back toward the ground. The result is thunder that feels out of sequence, arriving later and carrying longer than your sense of distance expects. In deep cold, that roll can travel across neighborhoods and fields, slipping around corners and over drifts, riding the stratified air as if it had a path laid out for it. What builds this charge in the first place is motion, and winter has a special way of making vertical motion out of a landscape that looks flat. A tongue of warmer, moister air slides over a shallow dome of cold near the surface. That contrast sets up lift. The cold air cannot hold much water vapor, but the air above can, and as it rises and cools, droplets supercool and freeze on impact with other particles. Each collision sorts charge. Each collision primes the next. The storm structure stacks like a layer cake, but inside the layers, updrafts drive the assembly line of ice. Some of the strongest winter electrical fields set up near large lakes or coastlines, where open water keeps feeding heat and moisture into air that is otherwise frigid. Convection forms tall columns that act more like summer thunderstorms than the quiet snow you expect. The lake or ocean surface becomes a fuel tank, and the cold sky turns that fuel into an engine. Updrafts carry ice particles into levels of the atmosphere where liquid water shouldn't last. Yet there it is, supercooled and ready to freeze on contact, adding mass and charge to graupel. Once the charge separation grows too strong, a leader forms and a path completes. The strike unfolds within a muffled world. The snow takes the edge off the brightness, and the thunder spreads into a soft pressure wave that feels close, even when the strike was not. The sensation is electrical without the violence you brace for in summer. It's like watching power express itself in slow motion, even though the physics remains fast and unforgiving. These storms alter how we see distance and depth. A bright flash inside heavy snow removes shadows. Landmarks flatten. There is no clear horizon. The eye loses contrast cues that normally help judge scale, and the mind fills gaps with guesses. You can watch a distant glow pulse through the snowfall and feel sure it is nearby, then hear the thunder roll from far away. The order in which your senses receive information no longer matches the rules you rely on. Inside the cloud, Graupel and ice crystals continue their work. The collisions are efficient because the particles are different sizes and shapes, because the updrafts keep them separated, and because the storm brings them back together again and again. Charge transfer thrives on repeated contact in air that stays just cold enough to keep droplets liquid until they freeze. Every physical detail strengthens the imbalance, from the density of flakes to the speed of the rising column. The cloud becomes a device that charges itself. At the ground, the snowfall can switch behavior with subtle shifts in the column above. A small change in temperature aloft can turn fluffy dendrites into rimed pellets that fall faster. The sound of the city dulls. The sky keeps flashing. Your breath hangs in front of you longer than usual. Those small observations fit the same pattern. The air is stratified, the surface is colder than the layer above, and energy prefers vertical routes. Even the way your voice carries in the cold night points to the layered sky. Thundersnow also reorders time in small ways. Lightning flashes often look briefer in winter because the snow hides the branching structure of the channel. Yet the thunder can arrive stretched, like kneaded dough, its low end preserved better than its sharp crack. You can count the seconds and convert to distance out of habit, but the bending sound can trick you into misplacing the strike. The storm is not trying to fool you. It simply changes the medium you're measuring through. Stand under one of these storms, and you are beneath a tower. Cold air near the ground, warmer layers above, and a vertical conveyor that lifts and recycles ice. Horizontal wind matters less than in a typical snow. The storm's muscle is up and down. Air rises, cools, releases heat when droplets freeze and rises more. That feedback builds tall structures in the cloud, and the taller they get, the more chances particles have to collide and trade electrons. The architecture favors charge separation, and with it, lightning. At night, the flashes can turn the world blue-white and brief. During the day, they can vanish within the snowfall, leaving the thunder to tell you what happened. Either way, the signal is the same. Winter weather is not passive. It stores, it layers, it waits. Then it releases, not all at once, but in pulses that carry through the air and across the snowpack. When the final flash fades and the last roll of thunder thins into the cold, something else begins to move. The energy that charged the storm doesn't vanish. It cascades through the system. Precipitation drops its load into rivers already rimmed with ice. Pressure changes nudge surface waters. In lakes and along coastlines, wind and weight start to reorganize what lies beneath. The storm's vertical engine hands its momentum to the ground and to the water, turning the sky's temporary power into patterns that keep working out of sight. Follow the path of that transfer, and you reach a different kind of winter physics. Ice at the surface behaves like a lid, but acts like a participant. Rivers can back up under the sudden mass of new snow and slush. Lakes stratify. Near the underside of the ice, light filters in just enough to keep life running while gases gather below, held in place by the seal on top. The storm's charge and lift become weight and flow, and in that shift, winter reveals another set of rules entirely. So a storm that lit the sky with muffled flashes ends by pressing on water, pushing it sidewise and upward, and setting the stage for what looks like water defying gravity. The same season that softened the bolt and stretched the thunder will now rework rivers and trap bubbles in clear sheets. The energy that leapt between charges just moments ago begins to travel downward, into currents and under ice, toward a new set of winter experiments that the surface barely hints at. Water shouldn't hesitate, yet in deep winter, it does. A broad river slackens near a bend where broken slabs have jammed tight against a narrowing channel. The surface lifts as if held by a hidden hand. For a long minute, the flow stalls. Then the current nearest the obstruction creeps the wrong way, curling upstream, sliding past anchored ice like a film played backward. It looks like a broken rule, but it's pressure finding a new route. The jam acts like a temporary dam, raising the upstream water level until the only relief is sideways and, in spots, against the usual grade. What the eye reads as defiance is the system equalizing, inch by inch, through any gap it can find. Wind turns the effect from a local oddity into a wide push. When a steady gale drives across a broad river mouth, it presses the surface inland. The water level tilts, higher on the inland side, lower toward the open water. For a while, the whole column responds by sliding upriver near the surface, while the lower water strains to hold course. Add a loose field of ice riding that wind pressure, and the flows act like blunt oars, redirecting surface flow into side channels and harbor basins not built to handle it. Docks moan. Mooring lines snap taut. The river looks alive in the wrong direction, but once winds ease or the jam breaks, the surface drops and the current resumes its default path. Upstream, a second shock waits where winter has regripped the river. Ice rubble piles under bridges and at tight meanders where current accelerates and shoves fragments together. The stack thickens, locks, and grows dense. Water backs up behind this accidental wall, spills onto low banks, then sneaks upriver along shallows and inlets. The main channel appears to slow, while side channels fill from the wrong end. Watch long enough, and you see the cycle repeat. Pressure climbs, the jam pops in sections, the river lurches forward, then new shards rush in and rebuild the barrier with the next cold snap. It's mechanical, not magical. A feedback loop written in ice, wind, and slope. The oddities don't stop at the surface. Move out onto a frozen lake and, under the quiet, the water column has arranged itself into layers that refuse to mingle. Near the underside of the ice, water holds just below freezing. A few feet down, it warms toward 4 degrees Celsius, which is water's maximum density. That dense layer settles like a blanket over deeper zones, and the whole stack stabilizes. Winter locks in that order. Without storms to stir it or strong currents to fold it, the lake becomes a vertical archive where each band keeps its chemistry to itself. In this separation, oxygen lives mostly in the topmost layer, where thin daylight still filters through snow and ice. Algae persist close to that boundary and continue photosynthesis, even in short daylight windows, using light that scatters through snow cover. Their oxygen stays local, enriching a narrow strip while deeper water sees none of it. Far below, in near darkness, bacteria feed on sinking organic matter and pull oxygen from the water around them. Nothing lifts fresh oxygen down there, so the deeper layers drift toward scarcity. The longer the lid holds, the stronger the divide becomes. Nutrients begin stacking in the isolation. Phosphorus and iron release from sediments under low oxygen conditions near the bottom and slowly accumulate because no mixing carries them upward. Nitrogen compounds shift form as microbes work through what little oxygen remains, sometimes leaving behind chemical endpoints that signal a system running on its reserves. Each layer becomes a neighborhood with its own budget. Oxygen-rich at the top, nutrient-rich at depth, a lean middle dividing them. Even the temperature difference between layers becomes a barrier, stopping vertical exchange like a lock keeping boats on separate levels. Now look again at the frozen surface. Clear ice traps, small domes that pucker upward like held breaths. Methane seeps from the dark sediments below, rises through the stratified water, and hits the hard stop of ice. If the ice is new and flexible, the gas lifts the sheet a little and halts there. If the ice has thickened and stiffened, bubbles stack into pearled chains, each sealed in its own pocket. Weeks pass. The column below stays still while the upper ice thickens around the bubble train, turning it into a visible timeline of slow release. That sealed world grows calmer and stranger as winter deepens. With the lid on, even small motions matter. A faint current left over from autumn's last winds slides along the contour between layers and can't cross. The surface sees a weak pulse of oxygen from algae near the ice, but that surplus never reaches deep water. Down below, the oxygen meter ticks towards zero as respiration continues. Fish shift depth bands, seeking microhabitats where oxygen hangs on. Some cluster near springs or inflows that punch a thin vertical thread through the layers. Others retreat into torpor to stretch their reserves. The lake isn't dead, it's strict. Every choice must match the structure. The mechanics that make rivers hesitate now also shape these quiet basins. When cold raises density at just above freezing, water settles into its most stable arrangement, then stops fighting it. No storms, no mixing. The water keeps its layers like a filing system, waiting for a cue to reorganize. That cue won't come until the lid lifts and strong winds return. Until then, chemistry compiles itself in place. By late winter, the deep layers can reach extreme oxygen deficits. Bacteria keep digesting whatever sinks. Hydrogen sulfide can appear near sediments in lakes prone to prolonged cover, a sign of oxygen debt paid with different chemistry. In the upper band, algae still photosynthesize during daylight, storing energy in cells that will seed the spring bloom when mixing resumes. Carbon dioxide builds in the dark zones and joins methane beneath the ice sheet, both held by the barrier until thaw. When the first thaws trace cracks through the surface, the lake holds a backlog of change. The melt opens skylights, sunlight floods deeper. The thin cap slumps and flexes, and wind finally grips the surface. Then the reset. The column overturns, the oxygen-rich surface drops, the nutrient-rich bottom rises. Bubbles release in strings that pop like a fast drum roll. A season's worth of separation dissolves in days, and the biology of the lake reboots on the inventory winter kept sealed. Return to the river one last time. The jam that once reversed the flow breaks in a loud, physical rearrangement. Sheets lever up and flip. Blocks grind. The release sends a surge downstream as if paying off a loan taken in midwinter. The untrained eye sees chaos. The record shows a sequence. Wind set the tilt, ice built the dam, pressure raised the head, reverse flow relieved the strain, and eventual failure restored the gradient. For a few hours, a simple slope lost to a complicated lid. The rule didn't vanish. It made room for another rule to act first. Zoom out, and a pattern comes into view. Winter imposes structure. The river's backward pulse and the lake's layered stillness share the same cause. A rigid cover, a narrowed path, and a pause in mixing. That structure traps more than motion. It traps history. Every bubble sealed in ice marks a moment of gas release. Every layer in a lake preserves a record of oxygen use and nutrient storage. Every jammed reach of river maps where force gathered, how it moved, and when it yielded. Look through clear ice again at those captured domes of methane, tiny fossils of recent time. They wait under your boots, silent and exact, held in place by a thin ceiling that winter built hand over hand. They will not move until the season allows it. And when they finally lift free, the release will feed the water above, stir the air at the surface, and carry a record forward as the frozen lid gives way to the larger archive winter has been preparing all along. Snowfall looks like weather, but it behaves like a recording device. Each flake forms around a nucleus, settles through air carrying traces of its journey, and lands as a single data point. A storm writes thousands of billions of these grains at once. The layer they build carries a texture and density tuned to the temperature of the cloud and the humidity of the air below it. Wind scuffs the surface, then stillness preserves it. A cold snap hardens the top. The next storm seals it in. By spring, you can read a winter's worth of shifts by touch alone. Crust from thaw, powder from a dry front, granular rounds from a warm storm that cooled as it fell. This is not decoration, it is storage. As that layered snow survives from one season into the next, weight starts the transformation. Sharp crystals grind against each other, edges round off, and contact points weld. Air is pushed into pockets and stitched into throats that narrow with time. Fresh flakes become fern, grains the size of sand, locked in a matrix that still breathes. With more loading, those pores shrink until they seal, and the final air becomes trapped not as a smear, but as discrete bubbles. What was weather becomes ice with a timestamp. The compression is slow enough that an entire atmosphere is captured in cross-section. Dust from a dry year, sulfate from a distant eruption, pollen from regional plants, and gases that once moved through lungs and leaves before they were locked away. The change from powder to ice builds its own clock. In high accumulation zones, layers stack fast and remain distinct. In the interior of the great ice sheets, snowfall is sparse and the clock runs slow. Fern densifies over decades. Bubbles close at different depths depending on temperature and accumulation rates. The deeper you go, the older the air. That air is not a proxy, it is air. It carries the actual mixture of carbon dioxide, methane, and nitrous oxide present when it was sealed. Even fine details survive. The ratio of oxygen and hydrogen isotopes locked into the water molecules themselves, which depends on the temperature at the cloud where the snow formed. Warmer conditions favor heavier isotopes to a different degree than colder ones. Measured down a core, these ratios trace temperature swings with seasonal to millennial precision. Extracting that record looks less like meteorology and more like excavation. Teams work through winters and summers to drill narrow vertical cylinders that run down hundreds to thousands of meters. Each meter has a structure that you can see by eye. Coarse, sun-dulled summer grains transition into the finer, wind-packed texture of winter. Dust bands mark dry, windy episodes. Thin, pale horizons carry sulfate deposited after far-off volcanoes injected aerosols into the stratosphere. Some layers show ash grains large enough to identify with microscopes, tying an ice layer to a specific eruption year. The core travels sealed and cold to labs where the archive is read by instrument. Saws cut sections. Melters feed pristine water into analyzers. Mechanical squeezers isolate bubbles without contamination. The lab lights do not change the data. It was written long before. The chemical archaeology inside those cylinders reaches across systems. Pollen grains carried on winds from forests and grasslands. Large in winter layers, their shapes and species counts trace which plants dominated which regions at the time, which translates to moisture and temperature conditions on land. Dust composition and grain size reflect source areas and wind strength. Fine mineral profiles shift when deserts are wetter or drier. Sulfate spikes point to eruption timing and magnitude, aligning ice records to tephra layers in sediments and to tree rings that show growth suppression after large volcanic events. Even the density of individual layers carries weather information. Compacted summer layers and airy winter bands map storm intensity and timing as weight and void. Gases inside those ancient bubbles carry the loudest signals. Direct measurements of carbon dioxide and methane give curves that rise and fall with glacial cycles. These are not inferred from plants or shells. They are samples of the atmosphere itself. You can align peaks and troughs with the isotopic temperature record and see how greenhouse gases and temperature move together across cold and warm periods. You can resolve sharp spikes in methane tied to rapid wetland expansion or clathrate releases. You can see abrupt events, years when conditions shifted faster than slow-moving systems should allow, and trace how long they persisted before returning toward prior baselines. Snow also archives material from beyond Earth. Tiny extraterrestrial dust grains fall constantly, and their signal survives in concentration and isotope ratios distinct from terrestrial dust. In carefully dated sections, layers show differences in helium isotopes that track the flux of these particles between cold and warm intervals. The signal is small but persistent. It adds another thread to the tapestry, not just what Earth's systems were doing, but how material arriving from space varied through time. It sits beside changes in the composition of continental dust that reflect altered weathering or source regions between an ice age and the present warm period. The deeper the drilling, the more stark the contrast with modern experience. At depth, annual bands become thinner under pressure, but they do not disappear. Instruments recover signals through diffusion. You can still resolve seasons in places. You can still see the beat of storms, the breath of the atmosphere, and the long hum of climate. Some cores reach back hundreds of thousands of years. Others sample the last century with fine detail that catches industrial shifts in trace metals and chemistry that did not exist in natural settings before factories and engines released them. That means the archive spans natural cycles and human alterations in one continuous column. The continuity makes it testable. Correlations with marine sediments and lake cores confirm timing, while independent volcanic markers lock dates across records. It is tempting to think of ice as brittle and fragile, but as an archive, it is robust. It insulates itself. It keeps a stable, cold environment that slows chemical reactions that would blur the record. It seals a record of air within solid lattices that resist infiltration. Even when surface layers are reworked by wind or short thaws, the deeper record remains intact. Once buried beyond the reach of melt, the stack becomes a library that persists for as long as the ice does. The data flows one way, from the past to the lab, without exposure to new chemistry after the moment of closure. Reading the archive is not one method, but many. Stable isotope analysis on water molecules tracks source temperatures and moisture pathways. Electrical conductivity scans detect acid layers from volcanic sulfate. Laser particle counters size dust populations. Gas chromatography quantifies trapped greenhouse gases. Microscopes identify pollen and ash. Each technique turns a different facet of the same layers into numbers. Together, they build a timeline with both long averages and sharp edges. Weather and climate separate the way they do in life. Storms within seasons, seasons within trends, trends within regimes. This memory system resets itself continuously. The top layers accept new writing every winter. Even in places where melt occurs, the pattern of melt refreezing lays down its own markers, encoding heat waves and rain-on snow events as distinct crusts and ice lenses. Where accumulation is heavy, the archive grows rapidly and stays high resolution for longer before compaction blurs it. Where accumulation is light, the record is thinner but stretches farther back. Both are valuable. One gives fine snapshots of recent decades and centuries. The other extends the story deep into glacial rhythms. Calling ice an archive is not metaphor. It preserves information with a fidelity rare in natural systems. The atmosphere above may shift from day to day, but the air inside the bubbles remains the same mixture it had when sealed. Forests may burn and regrow across continents, but their pollen and charcoal in the ice fix a record of when and how often. Volcanoes erupt and fade, but their sulfate trails persist as thin, countable lines. Climate moves, pauses, surges, and reverses, yet the ice holds each state in successive pages. No storm can rewrite once the pores close. As drill bits descend into older, tighter ice, another thought enters. If air and ash can ride down the ages inside crystals, the possibility opens that something else did too. Snow preserved the chemistry of vanished climates, but some layers did more than store breath and dust. They might have kept dormant forms that can resume their work when the seal is broken and warmth returns. The moment a lab dish warms and a dormant cell begins to move is the kind of quiet event that unsettles the calendar. A bacterium sealed inside ancient ice starts dividing again, as if centuries were only an intermission. It had not been feeding, it had not been growing, it had simply waited, preserved in darkness and cold, holding its structure in a state that resists time. When the temperature rises and liquid water touches a membrane that has been rigid for ages, metabolism resumes. The organism reads its own DNA, builds proteins, and re-enters a world that forgot it existed. The ice, it turns out, did not hold a corpse. It held a pause button. The survival itself strains intuition because everything we know about decay depends on motion. Molecules bump into each other, enzymes fold and unfold, reactive chemicals trade electrons, and oxygen gnaws away at delicate parts. Cold strips the movement out of that process. At low temperatures, reaction rates crawl, membranes stiffen, enzymes lock into shapes that no longer fit. That should break life, yet some cells prepare for these conditions with a set of tools that keeps their internal architecture intact. They reduce water where ice would otherwise shred membranes. They bind to forming crystals to halt sharp edges. They pack proteins against each other like bracing a wall. Metabolism does not stop in a dramatic way. It dwindles to a trace so faint, instruments struggle to detect it. What looks like an impossibility has rules. Extreme dormancy follows a sequence. First, the organism pushes water out of vulnerable spaces or replaces it with solutes that interfere with crystal formation. Concentrated sugar alcohols like glycerol and amino acids such as proline raise the number of dissolved particles inside the cell. That lowers the freezing point and helps control where and how ice can form. Some organisms produce antifreeze proteins that bind to ice faces. This binding changes the geometry of crystal growth, creating curvature that prevents expansion and keeps water from migrating away from the cell. The membrane, which needs to stay fluid enough to reseal after stress, is protected by these solutes, which insert between lipid molecules and reduce brittle transitions. Then the chemistry goes quiet. Enzymes that normally convert fuel to energy become idle because the random motion they rely on has faded. Ion pumps across membranes, slow to a crawl. The cell's power factories pause. Reactive species that would chew on DNA are less active at these temperatures, and some cells add antioxidant molecules to mop up what remains. DNA-binding proteins wrap genetic material more tightly, shielding it from damage. In this state, repair enzymes still operate in short bursts when microthaws occur, patching damage before it accumulates. Over years and decades, that combination of less damage and occasional repair can keep the cell's blueprint readable. Ice exerts pressure even when it is not in direct contact. As water freezes outside a cell, it pulls liquid water out, dehydrating the interior and shrinking the cell. Without the right solutes, that shrinkage would crumple membranes and misalign proteins. Properly prepared cells avoid this by balancing osmotic forces with a controlled rise in internal solutes. The result is a glassy interior, a vitrified state where molecules are immobilized, but still arranged in a way that can restart function later. That glass is not decorative. It is a physical phase that turns the cell into a stable solid rather than a brittle ice rock composite. Permafrost extends this principle into landscapes. Frozen ground is not empty. It is a layered vault where plant fragments, spores, and microbial communities sit locked into mineral and ice matrices. Low temperatures keep enzymes slow and microbes quiet. Darkness prevents energy-harvesting reactions that would otherwise feed decay. Tiny films of liquid water can persist along mineral surfaces even below freezing, providing narrow channels for chemical exchange at a pace that barely registers. Genetic material remains in this archive alongside dormant cells, each protected by the same physics: low temperature, limited oxygen, and restricted mobility. When thaw arrives, release is not uniform. Some microbes close to the melting front switch on immediately. Others wait for moisture to rehydrate them fully. Spores sense cues such as temperature pulses and specific nutrients. Plant tissues that once sank into silt re-enter the carbon cycle, providing food for reactivated microbes. In that moment, the past touches the present through chemistry. Compounds synthesized long ago become fuel. Dormant organisms become competitors again. Some of these revivals resemble a natural seed bank, except the storage medium is ice and soil rather than seed coats and dry air. The permafrost archive also contains chemical stories. Organic matter decomposes slowly under cold conditions, forming intermediate products that accumulate instead of flowing rapidly to carbon dioxide. When thaw opens pores and pathways, gases trapped in ice pockets escape. The timing, concentration, and composition of those gases depend on how long the freeze lasted and which organisms endured. Methane generated under low oxygen conditions can build in bubbles that deform ice from beneath. As thaw progresses, the transition zone becomes a patchwork of chemistry: oxidized surfaces, reduced cores, and water pools where anaerobic microbes thrive. Dormancy at the scale of a single cell rests on physical principles that reach across biology. Lower temperature reduces kinetic energy. Lower kinetic energy slows reactions. Slow reactions reduce damage and consumption. Stability rises. The organism interrupts its own timeline by letting the environment turn motion down. It does not fight winter, it synchronizes with it. In deeper ice, where darkness is complete and temperature is steady, that synchronization can stretch from seasons to centuries. The ice's weight gradually compacts air pockets, but small volumes of saline or organic-rich liquid can linger at crystal boundaries, offering microhabitats where preservation remains compatible with eventual revival. There are limits. Freezing is not gentle if it happens quickly. Needles of ice can perforate membranes. Rapid desiccation can pull proteins out of shape. That is why so many survival strategies front-load preparation. Cells synthesize cryoprotectants before the cold deepens. They reorganize membranes. Some repair DNA in advance. The aim is not to stay active through the freeze, but to remain structured enough to restart after it. That restart is a cascade. Water re-enters, membranes soften, enzymes unfold to working states, ion gradients rebuild, and metabolism ramps from trace to functional. A dormant bacterium becomes an active colony. A preserved spore becomes a thread of fungus. A frozen community becomes a food web again. The reach of this phenomenon goes beyond microbes. Tiny animals with resilient life cycles can suspend activity for long spans by lowering water content and stabilizing cell parts as with sugars that form internal glass. Plant seeds buried in frozen ground can carry viable embryos across decades until conditions align. Even tissues that do not survive whole contribute information, as fragments of DNA remain stable enough in cold conditions to be sequenced later. The result is a composite time capsule of living potential and readable history. This is where winter's character becomes dual. The same cold that halts growth can also keep life safe. Low heat flow reduces chemical noise. Ice walls block predators and competitors. Darkness slows consumption by withholding energy. Preservation is not a byproduct, it is a function. What freezes today might germinate or divide far in the future, and what fails to revive remains as a record that still informs the living. The gate does not open for everything, but it remains there, safeguarding both dormant life and the data of past ecosystems. As thaw migrates downward each spring and refreezes in autumn, the boundary between motion and stillness shifts position like a tide through soil and ice. Each pass writes a new layer of information and sets aside a fraction of life for later. A bacterium that reawakens from deep time does more than survive. It stitches a line across centuries with one cell division. And as that microscopic revival spreads through the microbial community, winter's archive returns to work, moving molecules, cycling elements, and handing off energy that has been stored in place. That handoff is not confined to ground or glacier. The atmosphere above those thawing surfaces feels the change as gases move from storage to sky. Concentrations shift near the surface as trapped molecules enter air that is still layered by cold. And once those signatures rise into the flow, the story that began at the scale of a cell expands to weather, where winter's larger patterns pull and redirect entire storm systems across the continents. Snow looks like an ending. Storm passes, flakes settle, wind fades, and the world goes quiet. But once that white layer spreads, it starts doing work the sky will answer to later. A fresh blanket changes how sunlight hits the planet, how air masses move, and where storms decide to go. Fields, rooftops, mountainsides, each patch of snow flips a switch in the energy system, and the atmosphere reacts over distances larger than countries. What appears to be leftover weather becomes a blueprint for the next week's storms. The first shift happens at the surface. Snow reflects most sunlight that falls on it, and that bounce keeps the ground colder than it would be under bare soil or forest. That immediate cooling sends a ripple upward. The air right above that bright surface loses heat, grows denser, and pools in place. The pool spreads outward as a slow, heavy current, fanning into valleys and across plains. Weather maps show it as a surface high, but on the ground it feels like a steady, dry chill that undercuts whatever is moving in from elsewhere. With enough coverage, this cold dome becomes a steering wheel. Warm, humid systems approaching from the west or south meet the dense edge and start to bend around it. The bend is not a sudden wall. It is a long slope of pressure that deflects the path by hundreds of miles. A snowfield in one region can nudge a storm track in another, adjusting where rain and snow will fall days later. Farmers notice a narrow band of heavy snow setting up again and again along the same corridor. Pilots feel unexpected headwinds and tailwinds as routes cross those boundaries. The shape of that white map matters. Up in the mid-latitudes, there is another player, the jet stream. This fast river of air follows the line where cold and warm meet. When snow cools the land beneath one side of that line, the contrast sharpens. A sharper contrast boosts wind speed at the edge, and the jet warps more easily into big waves. Those waves can dip and rise far from where they began, carrying storms into unusual paths or holding them in place over one region while skipping another. The sky, in effect, reads the ground and adjusts. This ground-sky feedback grows stronger when the snow stays clean and bright. Fresh crystals scatter light in all directions, and the energy never sinks in. The air above stays cold through the day and colder at night. The longer that pattern holds, the easier it is for the next front to slide along the same path. A thin layer is enough to start it. A thicker layer deepens it. Regional forecasts end up influenced less by incoming systems and more by what the surface already decided to do with the sun. The effect does not stop at storm track geometry. It reaches into seasonal patterns. In years with deep, persistent snowfields across the interior of continents, the soil beneath thaws later and stays wetter when melt finally arrives. That moisture takes energy to evaporate, so spring warms more slowly. In some regions, that delay and the extra moisture shift the timing of later seasonal winds and rains. A winter pattern can echo into the next season simply by managing how much energy the land has to give back to the air. Small changes in the snow's surface can undo a lot of that. When dust or soot lands on snow, the surface darkens. The darker surface absorbs more sun, melts sooner, and exposes ground earlier. Exposed ground warms the air above it, weakens the local cold pool, and releases the steering grip sooner. River basins downstream feel it as an early swell of meltwater followed by leaner flow later in summer. Cities feel it as faster spring warm-ups and different air quality patterns than a clean snow year would have produced. A fine layer of particles on white fields becomes a lever for entire watersheds. On synoptic scales, the presence of snow can lock pressure patterns in place. A broad, cold surface, high anchored over snow-covered land, pushes dry air outward across thousands of miles and blocks moist air from entering. Storms skirt the edge and intensify along it as they tap the temperature contrast. If that contrast increases, the jet above strengthens in segments, and embedded waves carry the storms faster along the edge. If it weakens, the jet meanders and storms slow down, dropping more precipitation over narrower zones. Either way, the snow below sets the tone. Regional examples show how sensitive the system is. A heavy snow season to the north can set up colder, denser air near the surface that acts like a shallow dam. Moist systems moving poleward hit that dam and slide along it instead, delivering precipitation hundreds of miles away from the usual route. Over mountain ranges, snowfields feed cool air into passes and basins every night, creating local flows that stack into larger pressure features downstream. That layered influence is easy to miss from the ground and obvious from space. Snow also sets up feedbacks with clouds. A bright surface cools the air below cloud decks from underneath, changing the balance between mixing and stability. On some days, that keeps low clouds intact for longer, reflecting even more sunlight back to space and reinforcing the surface cooling. On others, the stable layer undercuts cloud formation, clears the sky, and lets radiative cooling run at night. In both cases, the snow surface is not passive. It is an active boundary that decides how much energy moves between Earth and sky. As the season advances, the difference between shaded and sunlit areas grows in importance. North-facing slopes hold snow longer, maintaining local cold pools that can connect across valleys at night. South-facing slopes shed early, creating warm patches that spawn breezes. Those small circulations stitch together and can tilt the approach angle of a front by a few degrees. That minor tilt shifts where the heaviest band sets up, and the band lays down new snow in the same corridor, keeping the feedback alive for another cycle. When coverage spans continents, the planetary signal becomes clear. The bright cap across high latitudes reflects a large fraction of the energy that would otherwise warm the land. The cooled air mass beneath spreads equatorward as a surface flow, while the upper-level winds respond by tightening along the boundary. Storms ride that rail, and precipitation patterns change on the downstream side of oceans and mountains. What began as local reflectivity scales up into the routing of moisture across entire basins and plains. This is why a map of snow cover is not just a record of weather that already happened. It is a control panel. Add a few centimeters of fresh, clean snow over a wide area, and you shift the energy budget in the pressure pattern. Remove that layer early, and you loosen the steering. Even thin coverage can keep the surface cold enough to rebuild at night, holding a region in a winter mode that resists change for weeks. The system favors persistence once the ground turns bright. The feedback loops make winter self-reinforcing. Reflective snow cools the air above it, which helps new snow survive the next sunny day, which keeps the air cold enough for the next storm to fall as snow rather than rain. The longer that loop runs, the more the jet stream organizes along the cold boundary, and the more storms follow the same tracks. Patterns settle in. They become the background conditions that people feel as an unusually snowy month or a quiet stretch with storms bypassing their region entirely. From orbit, the effect is stark. Storm bands curve around the edges of snow-covered continents, pressure systems stretch and lock, and dark patches where snow has melted open up as warm anomalies that alter the flow. Satellites track the shifting line between white and not white as if it were an isobar. In a sense, it is. It marks where the planet is reflecting energy versus absorbing it, where the atmosphere will run faster and where it will slow. As those storm tracks arc and slide along the borders drawn by snow, the path forward leads over sea ice and polar shelves. There, the white surface is not just reflective, it is porous and alive with chemistry. Salt rejected from freezing seawater drains through channels in the ice, and those hidden pathways begin to move water and heat in ways no open ocean can. From a distance, the Arctic Ocean can look like a single white sheet, a clean lid pressed flat against the sea. Up close, that surface hides a maze. As seawater freezes, the forming ice crystals push salt out. The rejected salt gathers in tiny pockets that connect into threads, then into a branching network of liquid channels. What looks solid is perforated by corridors as thin as hairs, and as long as your arm, winding forward, splitting, merging, and dead-ending inside what still appears, from above, to be a continuous plate. The ice sets the walls. The salt water stays mobile. The result is a living plumbing system threaded through a frozen shell. Those liquid veins do not sit still. When the air cools, the channels narrow and squeeze their content into knots of brine. When temperatures ease, they widen and release, letting the brine relax and move. The network breathes with the weather. Every small drop in temperature raises the salinity inside those tunnels because water freezes out and salts remain behind. The chemistry shifts hour by hour. The oxygen thins as microbes use it faster than it can diffuse through tight passageways. The brine grows saltier than the surrounding ocean, enough to create conditions that would stress open water organisms. In these cages, chemistry becomes selective, favoring only those life strategies that can operate with minimal oxygen at high salinity and low temperature. Within this grid of liquid threads, life finds footholds. Cold-adapted bacteria line the channel walls and feed on dissolved organic matter pulled in from the sea below. Ice algae settle as films and sheets, binding to the inner surfaces like paint on rough plaster. These organisms use what little light filters through the snow and ice above. When the sun rises higher and days lengthen, photosynthesis begins not in the water beneath the ice, but inside the ice itself. Pigments capture the dim rays that make it through, and chemical energy starts flowing along the channels. Even though the space is narrow, nutrients move, wastes leave, and cells divide. The solid sea surface becomes a scaffold for narrow factories that work all winter and ramp up at the first hint of spring. The layout matters. Channel junctions collect particles and create tiny basins, while thin necks meter the movement of salts and gases. The ice's permeability changes with temperature, because only above a certain threshold do enough channels connect to allow flow from top to bottom. Below that point, the network fractures into isolated pockets that trap organisms and their chemistry in place. In movable sections, fluid leaks out and pulls fresh seawater in, renewing supplies of nitrate, phosphate, and dissolved carbon. In sealed sections, processes slow and oxygen can crash, shifting microbes to pathways that do not need much of it. Every centimeter hosts a different rulebook set by the geometry of ice and the small-scale choreography of freezing and thawing. Beneath the ice, the water is not quiet. Organic matter drifts down from summer blooms or arrives in pulses from coastal rivers before the freeze. Microbes continue to break it down through winter. In pockets where oxygen is limited, decomposition pushes toward methane production. Those methane bubbles rise until they strike the surface cap. Because the ice cannot vent them easily, they gather under the sheet in clear domes. One bubble joins another and another, building layers like stacked coins. The ice stretches upward over each pocket, turning the surface into a map of past biological activity. When the thaw arrives, the domes can release in quick bursts. Until then, they hold their records in place, each bubble a sealed note from the lake or the sea beneath. These domes do more than store gas. They press on the ice, changing stress patterns and guiding small fractures. They trap not only methane but also fractions of other gases rising from the water column. The timing and size of the bubbles trace changes in the food available to microbes, the presence of oxygen, and the temperature history of the water. If the winter stays long and the snow cover thick, the trapped gases grow more numerous and larger. If midwinter thaws crack vents, they discharge and reset the record. Each season writes a sequence that future conditions can erase or cement deeper, depending on how the ice evolves before meltout. Back in the brine network, chemical reactions keep redefining the interior ocean. As salts concentrate, the solution can reach compositions that precipitate small crystals of calcium carbonate, which dust the channel walls like frost on window panes. Where channel floors slope, brine drains downward under its own weight when it can, pulling newly formed salts and other dissolved compounds into the ocean below. Where the network pinches shut, the chemistry stalls and mineral crusts can build, coating surfaces where microbes once clung. But even as some corridors lock up, others open. The ice is never a single state. It cycles through permeability windows set by air temperature and the balance between freezing and brine removal. When channels connect from top to bottom, the heavy brine escapes. It pours out of the ice base as thin, dense plumes that fall like underwater rain. These sinking threads of cold, salty water slip into the upper ocean layers, then descend further because their density overcomes the surrounding fluid. Multiply that process across kilometers of sea ice, and the result is a field of invisible waterfalls. They feed the deeper limb of ocean circulation near coasts and shelves, where the effect is strongest. As they sink, they bring with them the chemical signature of the ice: concentrated salts, altered gases, and the traces of the microbiology that lived within. The ice that seemed like a barrier becomes a source, injecting distinct water masses that travel far from their origin. These brine outflows can carve tiny channels in the forming ice below, leaving textured patterns and filigree where the plumes met and refroze. The process reorganizes heat as well as salt. Each burst of drainage carries away cold, allowing the remaining ice to refreeze more quickly at the bottom. That feedback tightens the cycle. The more the brine drains, the cleaner the ice becomes, and the more it grows downward into the sea. The cold from the atmosphere does not just chill the surface. Through this plumbing, it reaches into the ocean. Interior, heat transport follows that path. The ice acts like a valve, controlling how energy moves between sky and sea. Life keeps pace with these shifts. When sunlight strengthens, algae in the channels bloom and release organic compounds that change the brine chemistry further, chelating metals and modifying surface tension along the walls. Bacteria respond to the new carbon by multiplying, even in the high salt core of the network. Diatom communities adapted to winter conditions become the seed stock for later open water blooms, once meltwater stabilizes the surface layer. The activity inside ice preconditions the ocean beneath, priming nutrients and setting the stage for bursts of productivity when the cap breaks apart. Many springtime events trace back to the slow, quiet assembly lines that ran inside ice in late winter. The threshold behavior of the network sets the tempo of everything. A night of intense cold can pinch off flow and trap gases. A day of milder air can connect channels, vent brine, and draw in fresh seawater. With each switch, oxygen levels rise and fall, salts concentrate, then dilute, and microbes shift their metabolic gears. The changes are small in any one channel, but large over a vast ice field. Scale binds the system together. Add wind, tides, and stress from moving flows, and the pattern becomes more intricate still, but the core remains constant. Salt rejection builds channels, temperature sculpts them, and life exploits the spaces left behind. All of this makes sea ice less like a lid and more like an organ. It exchanges fluids, it filters, it breathes, it builds gradients and releases them. It stores energy in the difference between frozen water and liquid salt, then drains that energy downward in pulses. It shapes the timing and strength of nearby currents, not only by blocking waves and wind, but by creating its own density flows that sink beyond sight. In that way, the white sheet on the horizon acts on the deep ocean without movement you can see from above. As the season advances and the sun sits just high enough to reach through snow, some channels glow faintly green with algal pigments. The network remains delicate. A single cold snap can freeze its throats. A warm wind can open its valves. That fragility meets stored force in the next act, when shifting temperatures and pressure will load the ice until it fractures and booms. The calm lattice that held centuries of chemistry and silent energy will face the stress that turns sheets into slabs and threads into cracks. The sound arrives before the reason does. A single boom rolls across the ice like distant artillery, followed by a tight, metallic ping that sprints away in a line you can't see. The lake looks calm. The sky is quiet, but the surface under your feet behaves like a stretched plate over liquid, storing strain until it snaps. In winter, that rigid sheet grows and shrinks with every shift in temperature. When cold sweeps in fast, the skin of the lake tightens. When sun returns or a warm wind passes, it relaxes. The ice cannot adjust everywhere at once, so the stress builds in silence. It holds, then breaks, and the break speaks. A chill of a few degrees is enough to set the entire surface in motion. Ice expands when it warms and contracts when it cools. Over kilometers, even tiny changes multiply into force. Tides can lift and lower the sheet, where a lake meets a river mouth or a bay connects to the sea, flexing the frozen surface like a slow breath. Beneath the ice, currents continue to move. That motion presses upward in some places and draws downward in others, loading the plate unevenly. The result is a frozen landscape that never truly rests. It bends without breaking until it can't, and then everything adjusts in a rush. The fractures don't wander, they fly. A crack can race from shore to shore in a shimmering straight line, as if someone drew a wire across the lake and plucked it hard. The sound changes with the thickness, the temperature, and the path. A thin sheet sings high and fast. A thicker one delivers low, rolling tones that travel far beyond the shoreline. The breaks branch into geometric patterns, each line a record of stress released and redirected. Where two sheets collide, or where wind piles one slab against another, pressure ridges form. Plates tilt and stack. Edges grind upward into angular walls that look like they were pushed by hands, but this is only the frozen record of forces meeting at speed. Sea ice builds the same structures on a grand scale. Where currents converge, the white surface buckles. Long ridges appear, full of broken blocks tilted at sharp angles, each block the remnant of a sheet shoved over its neighbor. Those ridges lock in mechanical energy that was once stored as tension and now persists as compression. They stand for weeks or months, creaking as temperature changes squeeze them tighter or loosen their grip. In calm weather, the groans are slow and constant. In a sudden freeze, they sharpen into knocks that echo across empty air. Storms leave their shape behind. When waves roll under a forming ice cover, the peaks and troughs press against the new sheet. As the freeze completes, those ripples lock into place like wrinkles in a sheet of steel. The water below keeps moving, but the top holds frozen profiles of past motion. Walk across it, and you can feel the surface rise and fall in long, regular swells. When temperatures swing or the ice softens near melt, those frozen waves can relax, releasing the strain in brief shudders that rattle the surface. The memory of wind becomes structure, then returns as a small tremor in the thaw. The physics depends on details you can't see. The thickness of the ice controls how far a vibration carries. A cold snap that drops the temperature by 10 degrees in a few hours can load the sheet quickly, triggering a day of pings and booms as different regions adjust. Pre-existing floors become paths for new fractures, guiding them along hidden seams set days or weeks earlier. The lake becomes a map of its own history, with lines that link last night's temperature swing to last month's stress, all stored in a material that looks plain and uniform from above. In the ocean, the story adds layers. As salt water freezes, it rejects salt into narrow channels. Those brine veins thread the ice, changing how it strengthens and how it fails. The channels can guide stress and concentrate weakness, allowing fractures to run along moist paths that always remain slightly different from the drier ice around them. When wind drives whole fields of ice against each other, the sheet behaves less like a single plate and more like a mosaic of moving tiles. Each tile bears loads from above, from below, and from its neighbors. Where tiles jam, the ridges grow. Where they pull apart, leads open as dark water appears between bright panes. The sounds tell you which process is at work. A long, low groan may mark a slow bending over a wide area. A rapid pop that repeats in a series can be a local crack propagating in steps as the sheet resettles. Sharp pings dart away along radial paths, their pitch rising as the signal outpaces its own echo. In polar basins, the noises can merge into a continuous chorus that seems to come from the horizon, because it does. Vibrations travel through ice and water with little loss when they match the right frequencies, and cold air bends sound back toward the surface. The frozen world broadcasts its adjustments in every direction. Pressure ridges act like miniature mountain belts. Compression accumulates along lines where motion converges. Blocks tilt and pile, then lock into a rigid ramp that resists more movement until the forces exceed its strength again. The geometry evolves day by day, driven by temperature cycles and wind. Eventually, thaw weakens the bonds. Meltwater seeps into cracks, reducing friction between slabs. A ridge can slump suddenly, releasing a brief thud that races across the sheet and into the water beneath. Even the collapse preserves a trace of the energy that built it, now redistributed as a small vibration fading into distance. Frozen waves hold a different kind of stored force. Their curved shapes act like bent beams. As temperatures drop, the ice contracts and tries to flatten the wave. As it warms, it tries to steepen again. The stiffness of the sheet resists both motions, building potential energy that sits quietly until something shifts. Wind loads, thermal gradients, the drag of currents under a narrow strait. Then a ridge may sharpen, a trough may deepen, or a fracture may jump the crest. Each adjustment is a negotiation between the material and the forces passing through it. The entire surface behaves as if it has been wound up. You cannot see the winding directly, but you can infer it from what follows: the sudden release, the elastic recoil, the wave of sound racing outward. A lake on a still night appears made of silence, yet its structure is tense. The stillness is only the visible part. Under the white skin, water moves. Above it, air cools and warms in cycles that never pause. The ice responds to both, adding and releasing energy with each hour as if it were the arm of a clock that stores the twist of a spring. Even small boundary conditions matter. A shoreline locks the sheet in place at the edges, concentrating stress along arcs that match the curve of the land. Islands create anchor points where cracks prefer to start or stop. Inlets feed currents that thin the ice or carve subsurface channels, weakening some areas while leaving others thick and strong. Bridges, rocks, and old pressure ridges act as supports or obstacles. This patchwork builds a specific stress landscape that leads to specific patterns of sound and motion when the next temperature swing arrives. By day, the sun's warmth can lull the surface into a quieter phase, widening a crack here, softening a ridge there. By night, the cold returns and the load resets. The cycle repeats across the season, adding faint lines to a dense ledger of mechanical events. A person crossing the ice hears a handful of them. The sheet keeps the rest as internal accounting. Every tone is a balance settled, a small correction on a structure that cannot stay perfectly still while the world around it moves. So the frozen water carries not only weight, but also stored work. The forces of wind, tides, currents, and temperature never disappear. They park in the ice as tension and compression, in ridges and locked waves, waiting for the next trigger. The outward calm is misleading. The surface is braced, not relaxed. It holds energy the way a raised mass holds gravity, with release always possible when a boundary shifts or a gradient tightens. When the last boom slides away over the horizon and the ringing pings fade into the lower register of water, the message remains. The ice has adjusted again. The ledger has a new line. And just beyond the edge of that bright sheet, the snow that falls now carries our own fine dust, drifting toward the same frozen record that has stored storms and seasons all along. Snow began taking our signature without asking. On the same silent flakes that once held volcanic ash and stray grains from space, it now collects soot from distant engines, threads of plastic worn from clothes and tires, and particles with a radioactive clock. These settle across polar ice the way dust settles on a bookshelf, layer after layer, indiscernible in the moment, permanent in the stack. Winter presses them down. Airy snow turns to dense fern, then ice. What fell last year becomes a line. What fell a century ago becomes a page you cannot smudge. We joined an archive that never closes. Those particles do not need to be near a city to arrive. They ride the long loops of air that drift over oceans and mountain ranges, across deserts and forests, thinning and collecting as seasons shift. Exhaust leaves a highway and ends up locked in a cloud over the Arctic. Fertilizer residues loosen from soil and become traces in the upper troposphere, later returning as barely measurable ions inside snowfall that no human will step on. Debris from nuclear tests launched decades ago still circulates in tiny amounts, dropping into storms that sweep clean coastlines where the only footprints belong to birds. The flakes look identical to ordinary snow. The chemistry says otherwise. As each winter storm forms, it acts like a collector plate. Fine particles and gases cling to ice crystals as they grow, wedging themselves into the crystal lattice or hitching a ride on their surfaces. Synthetic polymers, too small to see, nest among the grains. Metal particles from industry bind to the same places that naturally hold sea salt. By spring, the pack is a layered array of distinct signals. A pale band of late-season snowfall with fewer impurities, a darker band from a storm that crossed industrial airspace, a thin stripe that carries a spike from a distant wildfire. Compression keeps them sharp. Time, instead of blurring, sharpens their edges. In a core pulled from that ice, a laboratory can track our era with a finger. Lines of lead from past decades taper as regulations came and went. Nitrate patterns trace the steady push and pull of agriculture. Microplastic distributions reveal not only the presence of polymers, but their changing composition as manufacturing shifts. A small peak of particular isotopes flags the moments when atomic tests dusted the sky. Each measurement is a line in a ledger, but the ledger is not written by people. It is written by snow and pressure. Beyond chemistry, winter works on our artifacts the way it works on stone. Roads in cold regions lift and buckle from frost, heave as moisture in the ground freezes, expands, and pries the pavement upward. What begins as a hairline crack becomes a raised seam that collects drifts, then a ridge that channels meltwater and grows again the next freeze. Over years, an abandoned lane turns into a low wall that guides wind, snow, and seeds. The cold does not just keep it, it reshapes it. Farther north, on airstrips and training grounds that were never fully cleared, equipment sinks with each thaw and freeze, then locks in place as permafrost holds the soil like concrete. A track left by a heavy vehicle becomes a frozen trough that fills with snow and persists long after the vehicle is gone. In glaciated valleys, objects that fall or are left behind begin a slow migration inside the moving ice. They descend under snow accumulation, enter the conveyor, and travel with the glacier. Years become decades, decades become routes across unseen terrain. When the glacier thins or retreats, it releases them in a different place, as if the ice had filed and reissued them. At sea, ice can claim entire ships. When winter spreads a thick sheet and wind forces pack ice into pressure ridges, a vessel trapped in the field becomes a passenger of the wind and current. The ice carries it, rotates it, leans it on its side, buries it in snow, then drifts for months or years. When a summer breakup occurs or a warm shift opens leads, the wreck emerges and moves again, sometimes hundreds or thousands of miles from where it locked in. The map for these movements is not the ocean alone, but winter's mechanics etched into the surface. Wind fields, pack compression, and the slow choreography of freeze and melt. Even our most ordinary dust now records itself in frozen ground. Permafrost layers hold soot and chemicals just as old layers hold pollen and charcoal from ancient fires. A pit reveals stripes that look like wood grain but read like a timeline. You can point to a thin, dark zone and know it marks a distant eruption. Now, right next to it in younger layers, you find the markers of our century. Polymer fragments, industrial metals, traces of combustion that match known technologies. The past and the present share the same draw. This is not only about contamination. It is about how winter converts human presence into geology. Snow does not care about intention. It sorts by size, by charge, by affinity for ice, and then applies pressure. The result is a stack where natural and human signals sit together in fixed order. Future researchers do not need stories to know what we did. They can read it as a sequence. When certain plastics first appeared, when certain fuels were used most, when emissions dipped, when they rose again. The preservation window is long. Layers buried deep enough will not melt for centuries, sometimes longer if regional climate and accumulation rates hold. Each cold season adds to the archive and seals the last. Even in places where summers grow warmer, the highest interior ice and long frozen soils keep much of their contents. The material that fell with last winter's storm may outlive roads, buildings, and languages. It will sit in the same company as older layers that hold compressed air from climates that predate cities. Artifacts that seem too large for archives also find their way in. Communication lines, once laid in shallow trenches across frozen ground, become fossils threaded through permafrost, visible as disruptions in the soil structure long after the cables themselves decay. Metal drums and containers left on ice shelves tilt and slide as the surface creeps, then tip into crevasses and become part of the slow, internal landscape. Even footprints pressed into snow on cold, clear days can harden and survive within wind-compacted layers, their ridges and hollows preserved until a thaw or a storm erases the relief. Some persist long enough to become features in the snowpack, directing new snow and scouring wind into shapes that repeat the original imprint. The reach of this record extends into the oceans. Sea ice collects and concentrates particles from air and water at the moment of freezing. As brine drains through channels, it drags fine material into pockets where it remains until the flow melts. When it does, that pulse of concentrated material sinks or disperses and can settle on the seabed. Over seasons, this export leaves a faint but persistent line on the ocean floor that matches what the ice once held. Our trace enters marine sediment the way volcanic glass shards and diatoms have for ages. Small, but legible to anyone who knows where to look. What makes this all striking is how neutral the process is. The same system that preserved pollen from forests that no longer exist now preserves fibers from clothing and soot from engines. The same winter that held meteor dust holds fragments from a tire. In daily life, everything feels transient. In the ice, nothing is. We are temporary in experience and permanent in the record. Stand on a field of unmarked snow and you stand over a library that just added another thin shelf with your era's handwriting on it. The entry is not a paragraph. It is a pattern of ions, particles, and isotopes spaced by storms and set by temperature. It waits in the dark under a cover that gets heavier with each passing week. As those layers press together, our lines sit beside the planet's older marks. A band of silica from a long-vanished dust storm, a thin soot layer from a far-off forest fire, a pulse of sulfate from an eruption that no one wrote down. The ice keeps them all with the same method, the same mechanism that has been steering sound, light, water, life, and weather through winter, has also been filing away everything we shed without noticing. And the force doing the filing has a simple engine that runs every cold season, moving energy and matter into order, while the planet exhales its heat into space. Cold is not absence, it is direction. Everything we have seen, sound bending over ice, light stacking into pillars, metals tightening, animals reprogramming, are signs that energy is moving the same way water flows downhill. Heat disperses. Gradients flatten, systems slide toward balance. When winter arrives, you are watching the planet choose the fastest path toward equilibrium, using every tool it has. Reflection, radiation, stillness, storage. The season is not a mood, it is a function. Earth's tilt starts the exhale. The northern or southern hemisphere leans away. Sunlight arrives at a lower angle, and the surface absorbs less energy per square meter. Nights lengthen so the planet radiates for more hours than it receives. The math flips, heat escapes faster than it comes in. That single asymmetry drives everything that follows. Air cools from the ground up. Oceans release stored warmth. Land surfaces shed energy into the open sky. Ice forms not because cold appears, but because heat leaves. As energy drains, pressure differences sharpen. Cold air is dense, so it sinks and spreads. That spreading mass presses on warmer air at the edges and builds wind fields that scale from breezes to continental weather. The same loss steepens temperature gradients between snow-covered regions and darker ground. With stronger gradients, the atmosphere accelerates its own mixing, spawning storms that act like conveyor belts, moving heat poleward and cold equatorward. Winter storms aren't accidents, they are maintenance, machines built by difference to erase difference. Oceans feel the pull in other ways. At the surface, cooling makes water heavier, so it sinks, dragging oxygen downward and pulling nutrients up somewhere else. In polar seas, the formation of sea ice kicks salt into the water that remains, making it denser still. Those brine-heavy waters plunge and slide along the seafloor, feeding deep currents that can take centuries to complete a circuit. One loss of heat near the surface reorganizes chemistry and motion thousands of meters below. Ice, in this view, is not a cap, it is a valve. On land, winter flips material behavior because less thermal energy leaves fewer pathways for motion. Atoms in a steel beam vibrate less and settle closer together. That tiny contraction adds up across long spans until bridges groan and rails shift. Rubber chains stiffen as molecular segments lose the wiggle room that made them stretchy, so tires quiet and gaskets leak. Oils thicken, friction rises, and machines slow. None of this is mood or metaphor. It is the same directional rule expressed at different scales. Remove energy, reduce motion, expose structure. Life answers the same signal. Enzymes run slower when fluids thicken and molecules collide less often. So cells either generate heat, change their chemistry or pause. Some let ice form in controlled zones. Some drain water to avoid shards of crystal. Some drop metabolism to a trace so low that the difference between living and not living narrows to a line only chemistry can see. These are not quirks of particular species. They are solutions to a universal problem: how to keep information intact while motion fades. Snow and ice then amplify the flow. Bright surfaces reflect far more sunlight than soils or forests, sending incoming energy back before it can warm the ground. That reflectivity forms a feedback. More snow means more reflection, which means more cooling, which invites more snow. At the same time, a deep snowpack slows the loss of ground heat by trapping still air. It is a paradox that matches the engine's logic. Reflect out what you can, conserve what you must. Winter is efficient because it is selective. The engine does not stop at Earth. On Mars, thin air and distance from the sun mean the exhale dominates most of the time. Frost creeps across dunes, and carbon dioxide locks itself into polar caps each winter. Europa and Enceladus carry global oceans hidden beneath ice crusts, where heat from within meets cold from space, and a permanent version of winter sets the rules for chemistry and motion. Titan's haze, methane lakes, and slow seasons run on similar gradients. These are not exotic exceptions. They are the cosmic default when starlight is weak or intermittent. The same thermodynamics write different landscapes with the same pen. What this reveals is simple and sweeping. Winter is the surface shape of balance seeking. Pressure gradients form because energy wants to spread. Storms spin because gradients create pathways. Ice grows because energy can leave faster through solid water than through its liquid form, restructuring molecules into a more stable pattern at lower temperatures. Biological suspension works because reducing motion protects complexity. Each effect emerges from the same rule applied again and again until the planet, for a few months, runs in a different gear. This is also why winter serves as a recorder. Heat erases by stirring. It breaks, mixes, and diffuses. Cold preserves by quieting. It holds, separates, and stacks. A layer of snow seals yesterday's air in small pockets. A freezing lake cages gas below a clear lid. A glacier gathers the remnants of seasons, compresses them, and stores their chemistry in a stable lattice. Lower temperature reduces the number of possible moves a molecule can make, which is another way of saying it reduces the ways information can be lost. Memory grows in stillness. The longer the night, the stronger the exhale. Under a clear sky, ground surfaces with high emissivity radiate strongly in infrared, dropping temperature quickly until the air above decouples and stratifies. That stratification builds the inversions that carry sound across valleys and gather chemistry near the surface. Although it feels local, it is powered by the same planetary math: net radiation negative, energy leaving, structure settling into place. Even the booming cracks racing across a frozen lake follow from this. The ice plate contracts under falling temperature, stores mechanical stress, and releases it in lines that travel faster than you can track with your eyes. Stored energy seeks relief. Fracture is the root. If we step back to the largest frame, the pattern tightens further. Planets take in short-wave radiation and emit long-wave radiation. Over long spans, intake must match outflow or temperatures drift. Snow and ice help manage that account by adjusting reflectivity, while circulation moves heat from where it accumulates to where it can depart. Winter is the fiscal quarter when the books are balanced aggressively. The planet clears inventory. Heat in the oceans, moisture in the air, chemical gradients in soils and lakes. The cold engine is accounting, made physical. On worlds where intake stays low year-round, the archive deepens. Cold stabilizes molecular arrangements and slows reactions to a crawl, so even delicate compounds can persist for geological spans if sealed away from light and liquid water. The principle scales cleanly. Less motion, more preservation. When we find ancient air in ice or intact structures in frozen ground, we are reading a record kept not by chance, but by rule. So cold becomes more than a season. It is a memory mechanism the universe uses wherever energy can escape to open space. Heat blurs detail by constant rearrangement. Cold keeps edges sharp by withholding motion. Winter is that principle made visible in neighborhoods and forests, on rivers, and in the sky overhead. It is the part of the cycle that restores contrast. As the long night continues and the planet radiates into darkness, everything we have followed, sound, light, materials, storms, biology, settles into the quiet order the cold engine prefers. And from that wide frame, the view narrows again, back toward the smallest carrier with which this all started, the tiny solid that turns falling vapor into a pattern and gives the exhale a shape you can hold for a moment before it melts. Snow is falling again, and the flakes are carrying stowaways. Each crystal drifts down with a speck from space sealed inside. Material older than Earth's mountains, older than our cities, older than our maps of climate and time. It's the same snowfall we've walked through 1,000 times, but now every flake is also a receipt from the solar system, printed in ice and delivered to the ground where the planet files it away. Those particles begin far beyond our weather, moving through interplanetary space as dust too small to burn up, riding gravitational currents and solar wind for ages. They move quietly, without glowing trails or noise, until they meet the upper atmosphere. Most are only a few micrometers wide, small enough that friction can't tear them apart. They slow, they drift, and in the cold layers of the sky, they become something else's foundation. Water vapor condenses, builds structure, and locks onto the grain. A snowflake grows around a visitor from space. The path continues downward through layers of air that have been reorganized by winter. That matters. Calm, stratified skies help hold tiny particles in place long enough for the crystals to form and fall. Even on blue sky days, ice can precipitate out and align in halos around the sun, and some of those crystals carry the same interplanetary cores. When the flakes land, most people see only a surface. The planet sees an intake. Snow accumulates, it compacts. The top layer presses the one beneath it. Open spaces collapse. Air gets squeezed and stored. The foreign grain remains inside, now buried among local dust, ash, and trapped atmosphere. Time begins to work. Weeks become years. The clean geometry of snow transforms into firn, granular, dense, still permeable, but enough pressure builds that pathways close and pores seal. What was air becomes bubbles. What was drifting grain becomes a fixed marker in a three-dimensional record. Add more years, and the firn crosses a threshold into true ice. The record hardens. Chemistry stops moving. The archive is set. Hidden in those layers are fingerprints that link Earth to space in a measurable way. Some of the grains arrive with helium attached from their trip through the solar wind. That helium has a rare isotope that appears in far higher proportion in extraterrestrial dust than in terrestrial sources, making it a clean tag. Decades of cores show that this flux continues through glacial and interglacial cycles. Even shifts in the more common helium isotope point to changing origins of Earth dust as climates switch modes. The longer the record, the more the patterns stand out, and the more precisely we can see how constant the cosmic input remains while conditions at the surface rearrange. So a snowflake becomes a device. It captures interplanetary material at the moment of formation. It locks it into a lattice. It delivers it to the ground. It joins a layer that will compress, seal, and hold that grain as the planet's ice slowly thickens. Volcanic ash falls in different years and settles nearby. Sea salt sprays and drifts inland with a storm from another season. Microscopic shells from marine plankton ride winds across oceans and find the same resting place. And now, more recently, microplastics and industrial aerosols fall alongside them. Every winter adds pages. Every year closes them tighter. The same mechanism that stores these materials also keeps a careful log of the air itself. As the fern seals, tiny bubbles preserve past atmospheres with dates written in snow above them. That includes gases we care about for climate, but it also quietly includes the helium signature that signals cosmic dust. The line of evidence is not loud. It's steady. Layer by layer, it shows that space dust has arrived at the surface, been captured, and remained accessible to the present for study. This archive is not limited to Earth. The underlying engine is energy loss. When a world sheds heat faster than it gains it, the cold organizes matter. On Mars, thin air and long winters preserve frost in polar caps that hold seasonal records of dust storms and solar cycles. On Europa, a shell of ice covers an ocean. That shell fractures, refreezes, and traps chemical traces of the surface and space above. Titan hosts methane clouds and hydrocarbon rain under a deep freeze where lakes and dunes cycle slowly. Cold takes motion out of the system just enough to save structure. It slows reactions, narrows pathways, and keeps signals legible for long periods. Back here, winter does the same work on a human timescale. A lake freezes. The ice excludes salt or minerals into narrow channels if it formed from brackish water. In fresh lakes, it seals gas pockets beneath it and fixes them in place. Rivers carry tiny metal-rich particles, released by weathering upstream, and when snowfall intercepts them, the landscape files that evidence too. A storm across an ocean throws sea spray into the atmosphere, and weeks later, those crystals can land far inland, mixed with flakes bearing interplanetary cores. The sky's conveyor delivers, and winter's press binds. Trace the journey of a single grain. It leaves a parent body somewhere in the solar system and enters a slow orbit of chance. Solar wind bombards it with helium. It wanders for millennia. It intersects Earth's path and settles into the upper atmosphere where its small size prevents catastrophic heating. It drifts into a cloud where minute droplets freeze on contact and begin organizing around it. The crystal falls. It joins a snowfall that blankets a field, a forest, or a polar plain. Over seasons, the sheet thickens. Over decades, air passages close. Over centuries, pressure welds the record into solid ice. The grain no longer moves or reacts. It sits next to trapped air from a climate that has changed. It sits above a pulse of volcanic ash from an eruption no one alive remembers. It sits below the layer where soot from distant cities arrived, and below that where older aerosols settled during an ice age. It becomes part of an unbroken vertical library that links space to soil. This quiet process pays a second dividend. Because the deposition is continuous and the compaction rate can be reconstructed, the record has a timeline with fine detail. The flux of those helium-tagged grains can be measured through depth, showing when the rate of extraterrestrial material entering the atmosphere changed, stayed steady, or was masked by changing winds and precipitation. Combined with other chemical tracers, it becomes a cross-check on how Earth's atmosphere transported material across epochs. What began as a speck becomes a calibration tool for reading the entire archive with greater confidence. The scale problem dissolves. A flake that melts on your sleeve might carry a particle that will outlast your city. The frozen lake nearby isn't just a winter scene. It's part of a system that sorts, stores, and preserves. The layers beneath your feet don't erase the past. They compress it, fold it, and keep it legible for as long as the cold holds. Winter's stillness is busy. Its quiet is full. That first snowfall returns. Older now, not in age, but in meaning. The flakes are no longer just weather. They are couriers. They move data, where a storm came from, what the sky held, what space released, what the ground emitted last autumn, what burned on another continent, what factories released, what the ocean breathed. They also move time. As they accumulate, they change speed, turning rushing days into slow layers, slowing chemistry to a crawl, giving the planet a way to remember. The focus widens one last time. Cold turns up everywhere in the universe, and where it stays, information survives. It threads through ice caps, comet tails, frozen moons, and seasonal snow. It keeps the marbles, scratches, and fingerprints of processes that heat would scramble. When winter settles in here, the same rules apply. Energy drains away, motion eases, structure persists. Matter holds its form long enough to be read. A snowflake falls. It encloses a fleck from space. It nests inside others. The weight above presses down. The shape changes from soft to granular to locked. Years pass. The planet breathes under long night, sending heat outward while holding a record inward. There is no finale in this work. The process repeats. The file grows. The conversation between the ground, the sky, and space continues at a pace measured in winters. Silence returns, not as emptiness, but as the slow sound of the earth cooling a little more under clear air, writing what just happened into ice and letting the quiet carry it forward. The storm edge moves on. Flakes still drift in the halo light. The archive accepts them without hurry, and the night widens enough to hear the world exhale.